Hello friends, welcome to Susan and John MathTube. So we continue with complex analysis, and in today's video we are going to learn something extra important in many universities around the world. When you learn complex analysis, you will learn about the analytic function. And to prove a function is analytic is very difficult unless and until you learn the Cauchy-Reimann equation, and it's called the CR equations. And in this video we're going to learn the necessary condition for a function to become analytic, that is the CR equation. In your university they may ask you to learn the proof. Maybe for some applied mathematicians it might sound boring, but still it's nice to know what is actually happening in the things that you apply. Okay, let's start with the proof of CR equation. Once more let me tell you, I'm talking only about the necessary condition. It is not sufficient, it is only the necessary condition. Okay, so if a function is analytic, so here you are going to believe that the function is analytic, and then you are going to prove this. Once more, I am proving only one side. I am not talking about if and only if. I am talking only about an analytic function. If you give me an analytic function, then these equations will be balanced, and that is called the Cauchy-Reimann equation. Anyway, one warning: don't try to learn this proof without watching the definition of a complex function and the derivative of a complex function. Second warning: don't memorize the proof. It might take some time, because I know some students feel like, okay, in our university they ask the proof, so let's memorize the proof. That will actually, maybe you'll get mark, but that's not the right way. So it's a one-time investment. Take some time, try to understand the logic, and you'll never ever forget the proof. Okay, so let's start. So once more, let me put it like this. We are going to assume we have an analytic function. And in the last video I told you a function which is differentiable in each and every point in the domain is called analytic. And if a function is differentiable, then this limit will exist. So you can start like this. Assume let f of z equal to u plus iv be analytic. Do you still remember? Our input is x plus iy, and our output, the function value, will be represented by u plus iv. And if you want it to be a little bit more clear, the input will be uxy plus ivxy, because you are supposed to believe that the input is a function in x and y. I'll give you an example. Suppose f of z equal to z square. Then I'm going to call the output as u plus iv and the input as x plus iy, so that I'll get this. I will expand the right hand side and simplify. I think you still remember I square is minus 1. So we end up like x square plus 2ixy plus I square y square, and on simplification I will get something like this. Are you able to see u is a function in x and y? And similarly, v is another function in x and y. So I am going to call the function f of z equal to u plus iv as u x comma y plus I v x comma y, and I am going to believe that this function is analytic. Make it very clear. We are going to believe or assume that the given function is analytic. And since this function is analytic, it will be differentiable at every point in the domain. And the derivative is defined to be f dash of z. Can any one of you tell me? It's in the last video. Okay, we are measuring the change in the output with respect to the input, with respect to the change in input. And make sure we are talking about small changes. So this is the definition of derivative. Now I want you to remember the definition of the limit for complex valued function. Does it mean the left hand limit and the right hand limit should exist? No. Now look at this. Even if you approach a complex number from any direction, the value of the limit should be same. In real valued function, it was like so easy. The left hand limit should be equal to the right hand limit, or the left derivative should be equal to the right derivative. That means the derivative exists. But here, if all the limits exist, then the derivative exists. So once more, I am assuming the function is analytic. So this limit will exist regardless of the path. Okay, that's exactly what we are going to do. So once more, let me make it very clear. This limit will give me the same answer whether I approach the complex number like this, or from the left, or from the right, or from above, or from below, or like this. Okay, so we are going to get the same answer. I'm going to call it equation number 1. Now the logic goes like this. Listen very carefully. This is the input plane, the z plane, and this is the output plane. And let's assume this is our domain. That means I'm considering all the complex numbers inside this much space. And similarly, I'll get a range. Maybe it will be big or maybe it will be small, depends on the function. And the function carries all the input to the range. So I'll mark the function here. Now I'm going to consider one character, that is z. It can be anywhere. I'm considering the complex number z. And I'm considering another complex number z plus delta z a little bit away from this complex number. Now I have to make the distance between these two complex numbers very small. By the way, the point z will have an output. I'm going to call it f of z. And the point z plus delta will have an output, f of z plus delta z. It can be anywhere. I'm just assuming it's over here. Now I have to understand the change in the function corresponding to the change in the input. Can you see? This is the input, and the input increased a little bit. So the input can be here or here or here. I'm just assuming it's over here. So we are going to understand how does the output change with respect to the input. That's the definition of the derivative. Now I'm going to write case 1. In your exam, it will be nice if you make this figure. In case 1, I'll draw only the domain now. I'm not going to draw the range. In the domain, I'm going to call the point z as p. By the way, z is a complex number, x plus iy. And I'm moving to another complex number very near to z, which is at a distance z plus delta z, which comes to be x plus iy plus delta x plus I delta y, that is z plus delta z will be x plus delta x plus I into y plus delta y. Long back in lesson number 1, we learned about complex numbers, and we learned that every complex number should be simplified in the form real part plus imaginary part. Now look at this. Let's say this is z plus delta z. Now once more, let me make it very clear. We are comparing the change in the output with respect to the change in the input. Okay, provided the two numbers z and z plus delta z are very, very near. Now, in case 1, I am going to come nearer and I am going to call this point as Q. Imagine Q is approaching P. Q is approaching P means the distance between Z and Z plus delta will be very, very, very small. That means delta Z will be tending to 0. So I am going to move near P. So I'll go down. Going down means I'm going to cut the height. Can you see? This controls the height. And then I'm slowly going to move nearer and nearer and nearer and nearer and nearer. I'll stop here. I'll go very near. That means I'm making delta x tend to 0. So to understand this point, I'm going to approach, I'm going to move Q very near to P. How did I do that? I'm using two straight lines. I'm going straight down and then I'm slowly moving very near to Z. So delta y will be equal to 0 and delta x will tend to 0. Okay, now let's start. Now look at this. Do you still remember the definition of derivative? So I'm going to calculate the limit. So I'm going to calculate the derivative value. It is given by limit delta z tends to 0 f of z plus delta z minus f of z the whole divided by delta z. Now I'm going to simplify this. Look at this. F of z means u xy plus I v xy. You have to understand this point very, very, very well. So f of z plus delta z will be, look at this, z is x plus iy. The output will be called u x comma y. Can you understand? I am writing the real part and imaginary part of the input plus I into real part and imaginary part. Now can you see? I want f of z plus delta z. That will be u, what is the real part? X plus delta x, comma y plus delta y, plus I into v x plus delta x, y plus delta y. You think about it once more. Suppose my input is 6 plus 2i. Then the function value will be u 6 comma 2 plus I into v 6 comma 2. Now I am going to plug in this value, that is limit delta z tends to 0. So I hope you understood this step. So all I did is I took the value of the function at z plus delta z minus f of z. Okay, now I am going to do one more thing. Look at this. I told you I am going to work out the derivative in two different methods because the function is analytic, and if a function is analytic then the limit will be the same. That means the derivative value will be the same regardless of the path. So case 1, I am moving from Q, let's call this point as A. I am moving from Q to A and then from A to Z, A to P. When you move from Q to A, I am actually making delta y equal to 0 because this controls the height and this controls the x value. And I have to come nearer and nearer and nearer and nearer, and I have to come very near because we are talking about 2 points very nearby, Z and Z plus delta Z. Okay, so in the limit I am going to write delta x is very small and delta y is equal to 0. Now in the next step, I will plug in delta x. No, I cannot do that because delta x is only very small. But delta y I can write 0. So we get, okay, so I hope you got the point. I just removed delta y and I am making sure delta x is very small. Now I am going to rearrange this. Okay, so I hope you understood what I did. I am combining u and I am writing the imaginary part over here, and in the next line I am going to apply the property a plus b the whole divided by c will be a by c plus b by c. Now look at this. If you know a little bit of calculus called the partial derivatives, can you see what I have written here is the definition of partial derivative. Can you see? Partial derivative with respect to x means we are learning how the function changes according to x by keeping y as a constant. Look at this, delta x tends to 0, that means delta x is a variable, and we are learning how the function behaves when there is a movement in x and y is a constant. So the first part is the partial derivative with respect to x, plus the second part is the partial derivative with respect to x, and I am going to call it equation number 1. Let me make you understand the logic of the proof. We are trying to prove the necessary part. In the necessary part, we assume the given function is analytic. If a function is analytic, the derivative or the limit which gives us the value of the derivative will be the same regardless of the path q approaches p. Do you remember what is q and p? P means z and q means z plus delta z, which is a complex number very near to z. Now, in case 1, I am approaching q to a to p. That means I am cutting delta y and I am making delta x come very near to p. Now let's go for case 2. So please write case 2. In case 2, again I am drawing only the domain. So we have z and we have the complex number z plus delta z. This is our p and this is our q. Now I am going to approach q to p through a point called b like this. So what I did is I am going to make the change in x 0. Can you see? Look at this, x movement means in this direction. So I am going to cut down the x values and I am going to come nearer and nearer and nearer and nearer. I will never come, I will never coincide it with z, but I will be very near to z. That means I am going to cut down the height or make it very small. Okay, now I'm going to calculate the derivative value using this path. But don't forget, the given function is analytic. So the derivative that I calculate in case 1 and in case 2 must be equal. Okay, once more, what's the definition of derivative? Come on, try to write it yourself. Limit delta z tends to 0, change in output divided by change in input, and that will be nothing but delta z. Now, I hope you still remember that part. The given function is u plus iv, and the given input is x plus iy, and we have f of z plus delta z, and the same story. Now, I am plugging in the values. What is f of z? U plus iv. And what is f of z plus delta z? That is also u plus iv, but because of the difference in input, we get it like this. Now, in case 2, what is the name of our path? QBP. We are moving like QBP. That means I am going to cancel delta x, and I am going to make delta y very small, so that Q will be very near to P. Now, if you do this similar to case 1, this will be cancelled. So I get, okay, I'm skipping a lot of steps, but I'm sure you're smart enough to understand that. So what we did is we deleted delta x because that path QBP. So delta x will be gone, and then I collected the real part and the imaginary part. Then this will also be gone. I'm dividing it separately. Don't forget, a plus b by c can be written as a by c plus b by c. Now this I and I will get cancelled. Okay, now listen very carefully. Once more, if you know partial differentiation, the curly d, you can understand we are keeping x as a constant, and we are learning about the change in y, which is nothing but del u by del y, or the curly d, or the partial derivative with respect to y. Oh, by the way, can you see there is a 1 by I. 1 by I, when you simplify, becomes minus I. What is 1 by I? Minus I. So I can replace this 1 by I with minus I, and here I got cancelled, and I will get partial derivative of v with respect to y. So look at this. In case 1, the derivative value is something like this. That is, I'll write it like f dash of z equal to ux plus ivx. In case 2, I am getting the derivative value minus iuy plus vy. But wait a minute. What did we assume in the beginning? The function is analytic. If a function is analytic, it is differentiable at each and every point. And at each and every point, that limit will exist. And since the limit exists, regardless of the path, the value of the limit, that means what we got from case 1 and case 2, should be equal. So all we have to do is, I'm going to equate the value that I got from case 1 with the value that I have from case 2. But when will two complex numbers become equal? Of course, when the real part is equal to the real part and the imaginary part is equal to the imaginary part. And that gives me ux is equal to vy and uy is equal to minus vx. Think about it. Okay. And these equations are called the Cauchy-Reimann equation or the CR equation. And that's the end of the proof. If you like this video, share the video with your friends and family. I'll be back very soon with more videos like this. So till then, my friends, bye.